I'm going to talk about joint work with Antonio Laface of the University of Concepcion, Chile. And so I decided to divide the talk in two parts. In the first part, I will recall some definitions and known facts about Seshadri constant for surfaces. And then I will say something in the second part about the toric case. Okay, I will focus on the toric case. So the definition, we can define, well, we could give a more general definition, but just I decided to give this one for the case I'm interested in. So we take a projective surface, an F-line bundle H, which means that the intersection product with any curve is non-negative. And we can define the Seshadri constant of H at a smooth point of the surface by taking the intersection product of H with any curve passing through the point X and dividing by the multiplicity of the curve at the point. And then we take the infimum of all these rational numbers. In an analogous way, we can define the multiple Seshadri constant. Now we fix n general points on the surface. Okay, we just have to divide the denominator now is the sum of the multiplicities of the curve at the points. And we consider all the curves passing through at least one of the points. Okay, there is an equivalent definition. If we blow up the surface X at the point we are considering, we denote by E the exceptional divisor, then, well, the pullback of H is still an F, and so we start removing multiples of the exceptional divisors until we still have an F classes. Okay, so now the sup of this set it turns out to be equal to the Seshadri constant we defined before. Well, in an analogous way for the multiple Seshadri constant. And as a consequence, we can see that there is this upper bound for the value of the Seshadri constant, which is given by the square root of the self-intersection of H. Because, well, if we have an F class, then in particular the self-intersection is non-negative, and we can express this self-intersection as H square minus epsilon square, and so this gives the bound, the given bound. Okay, what happens when the Seshadri constant is strictly smaller than the given bound? Well, in this case, one can prove that there exists a curve which is called submaximal, which computes the Seshadri constant. Okay, so instead of having an infimum, we have a minimum. Okay, so in particular, the Seshadri constant is a rational number. Okay. By definition, we expect the Seshadri constant to be a real number, okay, because it is like a limit of rational numbers. But so far, there are no examples of irrational Seshadri constant, okay, no known examples of irrational Seshadri constant. And one last remark is that if we know the Neff cone of the blown up surface, then we can compute the Seshadri constant. Indeed, we need less because we just need to know the section of the Neff cone with the plane generated by the pullback of H and the exceptional divisor. Okay. Now, an easy example, which is the case of P2. First, we take one point in P2 and we take the hyperplane class H. Now, it is known that the effective cone of the blown up of P2 in one point has two extreme arrays, which are on one side we have the exceptional divisor E. On the other side we have the strict transform of a line through the point. Now, by duality, we can compute the Neff cone of the blown up P2 of the blow up of P2, which turns out to be this gray cone. The extreme arrays are the pullback of H, which is orthogonal to E, and again the strict transform of the line through the point. Okay, so well, we start from this NF class and then removing multiples of E. Well, the biggest value, the biggest multiple we can remove is 1. Okay, so the Seshadri constant in this case is 1, which is equal to the bound we gave before. Okay, the square root of the self-intersection of H in this case. And okay, in a similar way, we can compute the Seshadri constant, multiple Seshadri constant when the number of points we blow up is small enough, because if n is at most 8, well, it is possible to describe the effective cone of the blow up of P2 at n points. It is polyhedral, and again by duality we can describe the NF cone of the blow up. In particular, we can compute the Seshadri constants. Okay, I just remark that here the only values for which we get the bound, which is 1 divided by the square root of n, are n equal to 1, n equal to 4. Okay. In the other cases, the Seshadri constant is smaller than the bound. Okay. I draw here the picture in the case n equal to 2. Okay, so the effective cone is the big triangle, which is the extreme arrays are the two exceptional divisors, and the strict transform of the line through the 2 points. These are -1 curves. By duality, the NF cone is the small gray triangle here. So we have the extreme arrays are the pullback of H, and the strict transform of a line through the first point and through the second point. Here the dotted line is the plane generated by pullback of H and the sum of E1 and E2. So here we can see that the point where it intersects the NF cone, well, apart from the pullback of H, this corresponds to the value of the Seshadri constant, which is, well, this class is the class of a conic through the 2 points. And we can write as pullback of H minus 1/2 E1 plus E2. And so this gives the value of 1 divided by 2, this value for the Seshadri constant. As I told you, in this case, we have a submaximal curve, which is the line through the 2 points. Okay, if we consider the line through x1 and x2, the degree is 1, the sum of the multiplicities is 2, and so it computes the Seshadri constant. Okay, so when n is small, it's quite easy to describe, to compute the Seshadri constant. But when n is at least 9, well, in general, we do not know the value of the Seshadri, okay, the multiple Seshadri. I mean, we do not know apart when n is a perfect square, okay. There is a conjecture, Nagata conjecture, saying that the Seshadri constant, when n is at least 9, is always the biggest possible, which is the 1 divided by the square root of n, okay? But it is known only when n is a perfect square, okay? Well, this is equivalent to prove that the class, the Nagata class, which is pullback of H minus 1 over the square root of n sum of the EI is NF, okay? If we show that this class is NF, well, then the Seshadri is at least 1 divided by the square root of n. On the other side, we know the other inequality, and so it is equivalent to prove this conjecture, okay? I mean, it is an equivalent version of the Nagata conjecture. Now, if n is a perfect square, let's say n is equal to k squared, the idea is that we can fix a curve of degree k in the plane, and we fix n points on this curve, I mean k squared points, which of course, if we consider those points in the projective plane, are special points, okay? But anyway, we blow up P2 in this bunch of points, and we consider the strict transform of the curve C, okay? The class is k times, k is the degree, so k times pullback of h minus the sum of the EIs. And its self-intersection is 0 because we get k squared minus k squared as self-intersection is irreducible, so it is NEF. It is NEF on the blow-up of P2 at these special points, but one can reason now by semi-continuity to deduce that the same class is NEF also on the blowing up of P2 at the general points. Okay. And this is the content of Nagata conjecture, because we deduce that this class is NEF, and so the Seshadri is at least 1 divided by the square root of n, which is what we have to show. Okay. And right, one last example is the case of the weighted projective plane. Okay, so X is the weighted projective plane with weights A, B, C. These are positive integer numbers, and we can suppose that they are pairwise coprime. We take the blow up of this surface at the general point that I denote by E. We have that the Picard rank is 1, as in the case of P2. Okay, so we can take as a generator of the divisor class group, the class H, having self-intersection 1 divided by the product of ABC of the degrees. So when we blow up one point, we have 2-dimensional cones, okay, as in the case of P2. So in a sense, it seems to be an easy case, okay, because we have just 2-dimensional cones. But in general, the effective cone of the blown up surface in this case is unknown. We can say something because we can consider what is called the positive light cone Q, which is we can define Q as the set of classes such that the self-intersection is positive, and also the intersection product with an ample class is positive. Okay. And by Riemann-Roch, this cone is contained inside the effective cone of the surface. We have 2 extreme arrays. I denote by R plus and R minus these rays, which are the 2 classes of 0 self-intersection. Okay. So the pullback of H plus or minus 1 divided by the square root of ABC times the exceptional divisor. And well, there are 2 possibilities. In the first case, we have the effective cone on one side, we have the exceptional divisor. On the other side, it is bounded by the divisor R minus, the class R minus. And well, these, hypothetical possibilities, because this case would correspond to the Seshadri constant equal to 1 divided by the square root of ABC, okay, because by duality, the NEF cone, this would be the NEF cone. And so the class R minus would be an extreme array for the NEF cone too, okay? And this is equivalent to say that the Seshadri constant is 1 divided by the square root of ABC. In the second case, we have a class of a negative curve on this side, okay, on the left side of R minus, okay. By duality, the NEF cone is smaller, okay. We have this extreme array, which corresponds to a value of the Seshadri constant, which is smaller than the biggest possible. So this corresponds to a Seshadri constant rational, okay. Okay, so as I said, there are many cases in which it is known that there exists the curve C, negative curve C, as in this case. And apart from the case of P2, there are no known cases in which this happens. Okay, this happens. Okay. But it is conjectured that for some gradings, for instance, 9, 10, and 13, we are in this case, okay, in the first case. Right, but it is not known. It is not. And okay, in order to conclude the first part, I would like to go back to the previous problem, which is the Nagata conjecture, because there is this remark due to Kutkowski and Kurano if we could show that the Seshadri constant of the weighted projective plane is not rational, which means that it is equal to 1 divided by square root of ABC. Okay. Then this would imply that Nagata conjecture holds for this number of points, the product of ABC. Okay. So this would give the first example of Nagata conjecture for a number of points which is not a perfect square. Well, of course, I'm supposing that ABC are not all perfect squares. Okay, so this is not a rational number. Okay, and again, the idea is that we can consider this map from P2 to the weighted projective plane by sending a point xyz to the x to the 8th power, y to the b power, and z to the c power. This is a generical n to 1. Okay, where n is the product of ABC. Okay, indeed we have this diagram, okay, P2, commutative diagram, the weighted projective plane. Here we blow up the weighted projective plane at the point E, okay, the general point. Here over E we have n points, and we blow up P2 at this bunch of points. Okay, we can close this diagram. Let me call F tilde this map. Okay. Again, we are considering points which are in a special position on P2. Okay. But okay, our hypothesis is that the Seshadri constant is the biggest possible, which means that the ray R minus is F. Here, R minus is here. So we can consider its pullback in the blow up of P2 at these points, and it is still F. Well, it turns out to be the Nagata class. Okay, this one. We just have to reason, as before, by semi-continuity to deduce that the same class is F on the blowing up of P2 at n general points, and this is the content of the Nagata conjecture. Okay, so this is the idea to close the circle. Okay. Okay, so now I will focus on the case. I will try to go back to this problem at the end of the talk. Okay, but now I focus on the case of toric surfaces. Okay, so we can define a projective toric surface starting from a lattice polygon, which is the convex hull of a finite number of integer points in the plane. We denote by n the number of integer points, lattice points. And now we can define a map from the two-dimensional torus to the projective space of dimension n minus 1 by sending the pair st to the point whose coordinates are, well, the product of s to the 8th power times t to the b power, where AB runs through the integer points of the polygon, lattice polygon. Okay, so we take the closure of the image of this map, and we have a surface inside the projective space, and it turns out to be a toric surface because we have the image of the torus inside the surface. And okay, this is the toric surface associated to the polygon delta. Indeed, we can associate to delta the toric surface and also the ample class giving the map to the projective space. We will denote by L delta the linear system defined by the ample class H delta. As a notation, we will denote by E the general point of the toric surface, which is the image. We can take as E the image of the point 1, 1. So we get a point on the torus, and it is general in the sense that we can move this point around the dense open subset of the toric surface. Finally, I will use this notation given a integer positive number. I denote by L delta of M the subsystem of L delta consisting of the curves having multiplicity at least M at the general point. Okay, so, well, again, a couple of easy examples. If the polygon is this triangle, first triangle, well, we have 6 integer points. The toric surface turns out to be the projective plane. Well, one can see the toric surface by considering the dual fang of this polygon. Okay, this corresponds to P2. And the 6 sections are the section correspond to the conics of P2. So in this case, we are considering the 2 Veronese embedding of P2 inside P5. Okay. The second example is again a triangle, but we have just 4 integer points, giving a surface inside the P3. And well, this surface turns out to be a singular cubic surface of P3. Well, I just draw a bigger example, this triangle, because this triangle corresponds to the weighted projective plane P9, 10, 13. Okay, which is the weighted projective planes are indeed toric surfaces. Okay, and the ample class we are considering here is a multiple of h, which is just the product of the degrees times h. One more definition I need is the lattice width of a lattice polygon. Okay, first I define the lattice width with respect to a given direction, V, by taking the product of V, inner product of V with all the points of delta, and then I consider the maximum minus the minimum of these products. This is the width with respect to this direction V. And then we take the minimum possible of this width, and this is the lattice width of the polygon. Okay, for example, in this case, if I take the SB, I take 1, 0, okay? Then here I have the maximum, here the minimum. The difference is 3. So the width in this direction is 3. If I take this direction, okay, 1, 1, again, the maximum is taken here, it is 3, and now the minimum is here, and it's 1. So in this case, the width is 2, and indeed it is the smallest possible. So this is the width of the polygon. Okay. Okay, so now about Seshadri on toric surfaces associated to a polygon. We have to distinguish the 3 cases, because if the point we consider is either a point which is fixed by the action of the torus, well, in this case, when we blow up the toric surface, we get another toric surface. And so everything is known. We can compute the Neff cone and then the Seshadri constant. In the second case, the point is not fixed, but it lies on a curve which is fixed by the action of the torus. Well, in this case, when we blow up the point, the surface is not toric anymore, but again, it is possible to describe the Neff cone, and so to compute the Seshadri constant. So the most interesting case is the remaining one, which is when E is a general point. Okay, so a point which lies on the 2-dimensional torus. Well, there is a natural upper bound, which is the width of the polygon. And another result is due to Ito, who shows that there is also a lower bound. Okay, let me explain the lower bound by this example, okay, of the triangle I drew before. We can consider any projection of this triangle to a line. So in this case, I consider this projection onto the second factor. And then I take the length of this segment, which is 2. And we consider also the length of a section. Okay, so we intersect a section of this projection with the polygon. Okay, in this case, we get 2 and 3 divided by 2 here. And the result says that the Seshadri is at least the minimum between these two numbers. Okay, so in this case, it is at least 3/2. Okay. Okay, now I can state our first result. Well, the first one is just more like an observation. Okay, but anyway, we couldn't find in any paper, so we draw also this observation. Okay, we start from a polygon. We consider the Seshadri constant of the toric surface associated to the polygon and the ample class associated to this polygon and the general point. So the first result is that if the volume of the polygon is bigger than the square of the width, then the Seshadri constant is rational. Okay. By volume, we mean the normalized volume, which is twice the area of the polygon. Okay. And the second result is that if we can find a multiplicity M such that the linear system I defined as the curves of L delta having multiplicity at least M at the point is not empty. And moreover, we have this condition on the volume, which is smaller than or equal to M squared. Then again, we can deduce that the Seshadri constant is rational. And we also have this other bound, which in general is better than the previous one. Okay, the volume of delta divided by M. Okay, in most cases, this M is equal to the width. Okay, so if the volume is strictly smaller than the square of the width, then we have a better bound. Okay, with respect to the width. Finally, if we can show that there exists an irreducible curve inside this linear system, then we can compute the value of the Seshadri constant, which is the volume of delta divided by M. Okay. So just a few words about not all the proof, but just a pair of points. The first one is just an observation, because we know that the Seshadri constant is always smaller than or equal to the width of delta. Under our hypothesis, the width of delta is smaller than the square root of the volume. Okay. And well, there is a result saying that the volume of delta is equal to the self-intersection of H. Okay. So you can see that we have the strict inequality between epsilon and the bound we gave at the beginning of the talk. And so we are in the case in which there exists a submaximal curve, which means that the Seshadri is rational. Okay. Now, just let me just show this inequality in the second case. So we are supposing that this linear system is not empty, which means that if we consider the strict transform of an element of this system, we have this class in the blown up surface, which is the pullback of H minus M times E. M is the multiplicity at the point. So we have an effective class. And we know that the self-intersection, again, is H squared, which is the volume of delta, minus M squared. Now, since this class is effective, when we take the intersection product with, let me say, the Seshadri class, we have a non-negative intersection product because we know that this is Neff. Okay. And now we just have to write this product in a different way. So we sum and subtract M times C, so that here we get C. And then we get the C squared plus this multiple of E times C. E times C is nothing by M, okay? And so the inequality is this one, okay? In terms of epsilon, we deduce that epsilon is smaller than or equal to this quotient. And we know that M squared plus C squared is the volume of delta, okay, by this. This gives the inequality, right? Okay, this is the first result. In order to state some more results, I need to change a little bit the point of view. Okay, so now instead of starting from a polygon, we start from a polynomial. Okay, a Laurent polynomial in two variables, irreducible. And we consider delta to be its Newton polygon, which means the convex hull of the integer points corresponding to the exponents of the monomials of f. Okay. We denote by m the multiplicity of this polynomial at the point 1, 1. And now we can construct the toric surface and the endpoint class associated to this polygon delta. So we have the toric surface, the class, but we also have a curve, which is the closure of the zero locus of f inside the torus. And we call this curve, or better, the strict transform of this curve inside the blown up surface, we call an intrinsic curve. And the reason is that in some sense, we are considering this curve inside the most natural toric surface, which is the toric surface associated to its Newton polygon. Okay, so this is the reason of the definition of the intrinsic curve. Well, then we say that it is intrinsic negative if the self-intersection is negative, or the same for non-positive. It is in particular a minus n curve if intrinsic minus n curve if the self-intersection is minus n and the arithmetic genus is 0. And finally, it is expected if the number of integer points of the Newton polygon is at least the binomial n plus 1 over 2. Okay. A few words about this definition. Okay, first, the closure of this curve inside the toric surface is an element of the linear system we denoted by L delta of n, okay, by definition. So when we compute the self-intersection of the strict transform, we get again the volume of delta minus m squared. So when we say that the curve is intrinsic negative, we are just saying that the volume is smaller than m squared. And okay, we can also compute the arithmetic genus using the fact that this is the self-intersection of C, and this is the intersection of C with the canonical divisor of the blown up surface. Okay, we get the arithmetic genus can be expressed in terms of the geometry of the polygon, delta. In particular, for instance, when we consider an intrinsic minus 1 curve, well, we just have the volume must be m squared minus 1, so that the self-intersection is minus 1. And the number of points on the boundary of delta, integer points on the boundary of delta, is m plus 1. Okay, these are the two conditions characterizing an intrinsic minus 1 curve. And finally, we say that C is expected in this case, because if we look at the polygon delta, the number of integer points of delta is big enough to expect that there exists a curve having multiplicity m at the general point. Okay, so we expect the curve to exist. I mean, the linear system to be not empty. Okay, let me give one example. We start from this polynomial in two variables. You can see that it vanishes when u and v are equal to 1. And also its first derivatives vanish for u and v equal to 1. So the multiplicity at the point 1, 1 is 2. The Newton polygon is the triangle I drew before because, well, this monomial corresponds to these points, 2, 1, and so on, 1, 2, 0, 0. Okay, so this is the Newton polygon of this polynomial. The volume, which is twice the area, is 3, which is m squared minus 1. Okay, And the number of integer points on the boundary is again 3. We have just the vertices on the boundary, and which is m plus 1. So we are in this case, okay. Which means that f gives an example of an intrinsic -1 curve. Okay, so since we can see most of the properties of an intrinsic curve, negative curve, from the polygon, well, the first result about intrinsic non-positive curves is that we can classify all the polygons corresponding to intrinsic non-positive curves for any value of m at most 7. This is because there exists a database due to Balletti online, classifying all the non-equivalent polygons up to volume 50. Okay. And so since we are considering the square of m, okay, we can go up to m equal to 7. Here I just draw the picture for m up to 4 because then they are too many, okay. So this is the first result about intrinsic curves. The second is that if we just consider expected non-positive curves, then we have just 3 possibilities, okay? These 3 possibilities, which means that the self-intersection, for instance, can only be 0 or -1. We do not have expected -2 intrinsic curves, for instance. And well, this is again quite easy, the proof, because we just have to put together 3 inequalities. Okay, we have one inequality saying that the curve is non-positive. Okay, so the volume of delta is at most m squared. The second one says that the curve is expected. Okay, so the number of integer points is at least the binomial. And the third inequality is that the arithmetic genus is non-negative, okay, since this is an irreducible curve. We put together these 3 inequalities and the peak formula, which relates the volume of delta, the number of points of delta, and the number of boundary points of delta, okay. So putting together these the 3 inequalities and the equality, we get that these are the only possibilities. Okay. And finally, the final result about these curves, let me go back for a while to this. Okay. Well, you can see that if we consider an intrinsic non-positive curve, then we know that it is irreducible. It lies in this linear system, and it satisfies this inequality because it is non-negative. Okay, so we, as a straightforward corollary of this fact, we have that here. Anytime we consider an intrinsic non-positive curve, well, we can compute the Seshadri constant, which is equal to the bound we gave before. Okay, the volume of delta divided by the multiplicity. So in the example, again, of the triangle I gave before, well, we saw that there is an intrinsic -1 curve corresponding to this triangle. So we are in the hypothesis of this corollary. And we can compute the Seshadri constant, which is the volume of delta divided by m. So 3 divided by 2. Okay. And well, we were also able to find infinite families of intrinsic non-positive curves. Okay, so this means that for instance here, for any value of m at least 2, okay, this is the generalization of this case. Okay, for m equal 2, we have this triangle, but for any m bigger than or equal to 2, there exists an intrinsic -1 curve having this Newton polygon. Okay. Well, the same for the other cases. Okay, so we have these two families of intrinsic -1 curves, and this is in a way special because as we saw, there are no expected intrinsic -2 curves, and so this is a family of unexpected, okay, intrinsic negative curves. Okay. Well, the proof is not difficult, but I skip this proof because I want to go back to finish by going back to the problem, the initial problem. So how could well this definition of the intrinsic curve help in the problem of proving that the Seshadri constant of a weighted projective plane is irrational? Well, let us fix the case of 9, 10, 13, where we know that, well, it is conjectured that the Seshadri constant is irrational. So one would like to prove that the Seshadri constant is 1 divided by the square root of the product of 9, 10, 13. Well, this is equivalent to prove, this is the picture, okay. This is R minus. This is the ray whose slope corresponds to the Seshadri constant, so it is the irrational slope, this one. We would like to show that there exists an infinite family of rays inside the affective cone, approaching this from the inside this irrational ray, okay. And one can use a result of Hausen, Kircher, and Laface, which allows to, well, if we have, I mean, the general is more, the result is more general, but in this case, we have a toric surface. We blow up this surface in one point, okay? There is a way, if we fix a multiplicity, to describe a set of generators for the Cox ring of the blown up surface, okay? Of multiplicity at most m fixed. So the class of a generator for the Cox ring corresponds to an element of the affective cone. Okay, so this allows to produce classes inside the affective cone. And well, for instance, if we set m to be at most 30, we found this list of 52 generators. Okay, these are all positive curves inside the blow up of the weighted projective plane. But if we consider the curves inside the Newton, each curve inside its Newton polygon, well, here I wrote the self-intersection as an intrinsic curve. So you can see that there are many intrinsic -1 curves. Okay, all these are intrinsic -1 curves. Okay, so these are generators. These are elements of the effective cone of the blow up of the weighted projective plane. But if we consider them as an intrinsic curves are intrinsic -1 curves. Okay, for example, in correspondence of this degree, we have this is the Newton polygon of the curve. Okay, so I'm saying that if we consider the volume of this hexagon minus m square, we get -1 because this is an intrinsic -1 curve. But if we consider the volume of the, well, okay, we add these two small pieces, we get a triangle. So if we consider the volume of this triangle, which corresponds to the curve inside the weighted projective plane, well, it is bigger, we get a positive number. So it is a positive curve inside the blow up of the weighted projective plane. Okay, and okay, this particular case, this is the value of the, I mean the slope of the irrational ray, and this is the value of the ray corresponding to this -1 curve. So it is close, but not so close. But now I wanted to end with the I think a natural question, because we saw on one side that there are many intrinsic -1 curves appearing here. And on the other side, we saw that it is possible to construct infinite families of intrinsic -1 curves. Okay, so the question is it possible to construct an infinite family of intrinsic -1 curves approaching the slope of the irrational ray? Okay, of course, if I don't know the answer, because if this would be the case, then this would show that the Seshadri constant is irrational. Okay, so it is an open question. And okay, this is the end of the talk. Thank you for the attention. A bit of bibliography. Yeah.